Hi everyone, my name is Elliot McDonald, and today I'll be walking you through AMPL tutorial 2. When we create machine learning models, a common problem that we come across is the issue of overfitting the training data. A machine learning model that is overfit creates predictions that work very well on the data it was trained on, but very poorly on real data. Imagine a dataset where we're trying to find the relation between ice cream sales and temperature. We curate our data and train a regression model with the data. In a model that is well fit, we are likely to see a fairly linear response that is able to see the big picture that as temperature increases, ice cream sales will increase as well. On the other hand, if we have a model that does not fit well, our model will simply memorize the training values that it's already seen and create predictions that are very local to the memorized values. There are two popular methods that AMPL supports to combat this overfitting: three-way splits and k-fold cross-validation. Today we'll be talking about the three-way splits method. In three-way splits, we'll take the data that we curated in tutorial 1 and split it into 3 different subsets: training data, validation data, and test data. The training data is usually the biggest subset, and it is the actual data that we will use to train our model. You can think of training data as an example in a textbook that is used to help the student study for an exam. Then we have the validation data, which the model is not allowed to use or train with, and that way, when we run it against our model's predictions, we can be sure that it hasn't seen this data before and it didn't just memorize its values. We use validation data by running it against several possible machine learning models and picking the one that performs the best on the validation data. Validation data is like the practice examples that we use to determine what method we want to use to solve the problems in the exam. Lastly, we have our final exam, the test data, which is simply used to give us a final performance metric for the final model that we chose. The way that we actually divide up the data can be done in 2 different ways in AMPL. The first one is the more obvious method. We could just divide up the data randomly so that we have the percentage that we want of our curated data in training, validation, and test. It would ensure that all 3 of the subsets have the same variety of the types of molecules. The preferred way, however, is known as a scaffold split. In a scaffold split, we purposely group together molecules with similar scaffolding, and thus each of the 3 subsets are somewhat segregated when it comes to chemical families. By performing scaffold splits, we force the model to encounter entirely different types of chemicals in the validation and test sets than what they were originally trained on in the training set, which makes for a much more challenging process for the model. However, the result of this process is that models have a better ability to generalize to many different chemical families than you would normally get using a random split. There are 5 main functions that we will use to achieve a scaffold split. First, we will use our parser wrapper to prepare some arguments for our pipeline object initialization, and then we'll use that object to actually create our split. We will then use 2 other functions that will help us visualize the way that our automatic split performed so that we can verify its correctness. One of them is split stats, which will allow us to check whether the scaffold split made chemically distinct categories, and the other is a plot of the response distributions, which lets us check that the training output values are generally similar to the validation test sets, so that the model will be asked to predict an inhibition value higher or lower than that of any compound it's ever been trained on. Let's jump into the code to get a better understanding of how this works. The first thing that we'll need to do is to retrieve the curated full dataset that we put together in tutorial 1. So we import pandas and set up a string referring to the path from our Python file to the curated CSV that we saved, as well as a string for the directory that we want to place the results of our split in. In this example, we're just going to put the resulting split in the same directory as the unsplit curated data. We also set the logging setting to info level to reduce the number of log messages. Many of the functions that we will use in the AMPL pipeline have us input a parameter dictionary. For the split function, we will set a variety of parameters. We set the dataset key, which refers to the string to our curated unsplit data. We name the response, chemical ID, and smiles columns that we set in tutorial 1 in the curated data frame, as well as the string to the directory for our resulting splits to go into. We specify that the data hasn't been split yet, the type of splitting method we are using, and the fraction of the total data that we want to be validation and test data. The remaining 70% of the data will be training data. Lastly, we set settings related to featurization and training, which we will talk about in a future tutorial. To do the actual split, we need to import model pipeline and parameter parser so that we can wrap the parameter dictionary and submit it to a new model pipeline object before using that object to call split dataset. The output of split dataset is the name of the split table that has been saved in our output folder. By using glob and OS, we can search for files with that UUID in the name, and that way we can read in the split file that we just made. The split file data frame consists of 3 total columns: the ID of the compound, the subset it was assigned to, and the fold, which has to do with k-fold cross-validation. Displaying the value counts for the subset column, we see that as desired, about 15% of the data is now in validation set, 15% is in test set, and the last 70% is in the training set. Remember that the main point of using the scaffold splitting method was that we wanted to ensure training subsets were significantly different than the validation and test subset when it comes to chemical families. So we want to verify that the split actually achieved that. A handy way to measure the dissimilarity between compounds in the subsets is the Tanimoto distances with the EC-FP fingerprints. The compare split plots module can help us easily achieve this. We import Seaborn, Matplot, and compare split plots before reading in the curated dataset as a data frame and running split stats with the curated data, the split table, and the names of the relevant columns. We can then just take our split stats object and plot it using matplotlib to achieve a graph showing the differences between the training data and the validation data, as well as the training data and the test data. Since the majority of the Tanimoto distances are between 0.2 and 0.8, we know that training compounds are structurally different than most of the compounds in the validation and test sets, which tells us that we can trust that the models selected based on their validation set performance will likely be generalized and perform just as well to the test set. We also want to plot the distribution of response values in each subset to ensure that each subset has similar pKi values so that the model wouldn't be asked to predict a value from the test set with a pKi different than anything it's ever seen before. We do this by importing split response distribution plots and supplying the plot split subset response distributions with the split parameters. Since we can see that the pKi's are roughly similarly distributed across the subsets, we can be confident that this won't be an issue. We have now finished the process of splitting our data, and in tutorial 3, we'll lead you through the process of training a model using this dataset.